Wow, very seamless. So thank you guys all for coming. Thank you for having me. I really appreciate being here. My name is John Morra. I'm the Vice President of Data Science at ZEFR. So before we start, I'm going to do just a little intro on who I am and how I got here. I have an undergraduate degree in biomedical engineering from Johns Hopkins and a PhD from UCLA in the same. I founded my own company doing medical image processing, machine learning methods and medical image processing for radiation oncology patients. After I did that for a while, I joined eHarmony. This was back in 2013. I kind of looked around at the landscape and said, I know how to program, I know machine learning, hooray, I'm a data scientist. And started off at eHarmony doing image processing work there. Worked my way up to lead machine learning efforts at eHarmony, where we did matching models, pricing models, fraud detection, churn models, a whole bunch of other things. I then moved over to ZEFR. At ZEFR, I lead machine learning efforts, and we focus on video ad tech. So ZEFR really is, ZEFR's value prop is that we deliver contextually relevant video for ads. So if you want to go out and buy videos, we work primarily on YouTube. We hypothesize that when the ad and the content align, it's a better experience for the user and a better experience for the brand as well. So just one quick motivating example, and then we'll get all into the fun stuff. Imagine you're a mom, you have 2 young children, and you probably have many devices. Well, you have diverse interests. Let's say one of your interests is beauty products. So you like to go on YouTube and like to watch how to apply makeup, how to do shampoo or whatever. And when you're watching those videos, maybe seeing an ad for L'Oreal is right in line. And that's totally expected and not intrusive. But since you're diverse, you also like dirt bikes. And when you go and watch your dirt bike videos, seeing an ad for L'Oreal is really not a good experience. You wouldn't expect that. Well, you also have one device that you're constantly logged into that you share with your kids who love Peppa Pig. If you were to do only user-based targeting, you would get the same L'Oreal ad for all 3 videos, which really doesn't make sense. So with that in mind, ZEFR comes along and tries to solve this problem. So 2 open questions that we have at ZEFR are, first of all, what is the appropriate packaging? How do we package up videos in a way that our clients want to buy them? And then how do videos get assigned to that packaging? So one is, what do the clients want to buy? And the other is, how do the videos get into that packaging? So as the title of my talk is top-down and bottom-up, let's do a brief overview of exactly what that means. So on the top-down approach, we start by researching what sells. What is the market? What do brands and agencies, what do they want to buy? We break those high-level concepts into smaller labels. So we might have automotive, and underneath automotive, we might have luxury cars, we might have eco-friendly cars, and stuff like that. Next, we go out and assign labels to videos. So we want to scour all of YouTube and assign the appropriate labels to those videos. And finally, we want to calculate the size, the number of videos in each of those labels, so we know how much we can sell. Contrast that with the bottom-up approach, where we first just observe videos on YouTube. We have no preconditions. All we assume is that videos exist. Next, we cluster those videos to create labels and again find the sizes. This is totally driven by the content, not by what our clients actually want necessarily, which means we need to determine if those labels are valuable. Just because a concept exists on YouTube doesn't mean anyone actually wants to buy it. And finally, we sell those labels that are in fact valuable. So for those that are familiar with machine learning, you'll recognize the left as a supervised learning problem, and on the right, an unsupervised learning problem. So let's briefly go into some benefits and drawbacks of each of those. First, on the top down, they're curated labels. So this is really nice. So we know that these things are going to sell in the market, and frankly, it's easy to judge success. You know, your cross-fold validation, there's well-established metrics to say if you're doing a good or a bad job. But the drawbacks are we have to verify these label sizes. Again, a client might want to buy a concept that just doesn't exist on YouTube. And we also need to continuously curate the labels. You know, back in 2013, Ice Bucket Challenge wasn't a thing, and then it became a huge thing, and now it's not a thing again. So we had to know that to keep in front of all that. On the bottom-up approach, we have a better representation of what's on the platform, and we can surface new ideas quicker. So this is really a nice property of the unsupervised learning approach. but we do have to manually curate the labels, and it is difficult to judge success. Those familiar with the unsupervised learning literature will know stuff like perplexity, which is nice, but doesn't really mean you did a good or a bad job. So let's break it down and get into each of these individually, starting with the top-down approach. So here we have a video. This is an Honest Trailers video, which if you guys have not heard of Honest Trailers, I recommend it. It's hilarious. This is specifically one for Jurassic World. So what does our labeling look like at ZEFR? So we might label this as all movies, all trailers, comedy, Honest Trailers itself, that's a label we have, parodies, and science fiction and fantasy. So these are all the labels that would apply to this video. And it's important to note that this is a multi-label problem and not a multi-class problem. In multi-label, if we assume there's k labels, each video is assigned between 0 and k of them. It can be about nothing, it can be about everything. In multi-class, each video is assigned exactly one class. So if you're very familiar with neural network architectures, this is the difference between a softmax activation function for the multi-class side and multiple sigmoid activation functions for the multi-label side. So before I dive into exactly how we do that, I wanted to give you guys a flavor of what ZEFR's packaging looks like. So this is going to kind of fly around while I talk. And what we see is we have a two-level hierarchy where packages are our higher level concepts and labels in pink are our lower level concepts. And so as you watch this, you can see some of the things that we care about are very concrete, stuff like cars, and some are more wishy-washy, like seasons, right? Or like moms, like it's difficult, mom, DIY, and decor. Like that's kind of difficult to really assess in qualitative or quantitatively, excuse me. So what I wanted to do after I saw this was go ahead and see if there's any open source data sets. And I cannot recommend this enough in the audience. If you're a practicing data scientist and you're not using open source data sets or have researched it, you're probably not doing something right. So the first thing I did was I researched an open source data set and found one. It could not be more perfect for my use case. YouTube itself released something called the YouTube 8 million, which is 8 million videos that were hand-labeled according to Google's knowledge graph, which assumed freebase, of about 4,200 labels. Publicly available. You guys can go check it out. I think the link's on the bottom. And this is really nice. This was released in order to further computer vision research into video, which is still relatively in its infancy, but I wanted to use it directly for ZEFR's benefit. So what I did is engaged in a label-to-label matching problem, where I took the 4,200 labels provided by Google and mapped them to the 500 or so labels that ZEFR cares about. But we don't want to just learn what Google knows. We want to inject our own information because, first of all, we don't want Google's biases. And Google didn't have perfect coverage. Like they don't have a mom, DIY, and decor label. So we need to build that ourselves. So we're currently building a review queue where manual reviewers go in and they watch videos. And this one is for our brand safety, but it's going to be extended for all of our relevancy as well, where users go in and mark yes or no for these different things. And this becomes very important to ZEFR as this corpus grows. This is what we use to train our algorithm, but it's seeded with 8 million labels I get, or 8 million videos I get totally for free. So before I engaged in this, I wanted to see if this was even possible. So I did a nice visualization of a binary classification problem. So when you think of multi-label, you can decompose it into k binary classification problems if you have k labels. This particular one is hair versus not hair. So everything that's hair and everything else that's not hair. What you see is two axes. On the x-axis is words that are frequent in not hair. So words down here would be not frequent in not hair, and words on the bottom right would be frequent in not hair. The y-axis is frequency in hair. So what I'm going to do, and then the color is F-score. It's a measurement of how tight that correlation is. So what I'm going to do is zoom into two different quadrants. First, in the upper left quadrant, these are words which are, again, are frequent in videos about hair and not frequent in videos not about hair. So they are words that are more or less unambiguously about hair, like twist out or wig or braid or, well, some of them you can argue, but you see a lot of words that kind of make sense here, right? And the point of this visualization is to show, does the data that I'm looking at, can it solve the problem? So then we look in the upper right quadrant, same graph. These are words which are frequent in both hair and not hair. So you see words like DIY or wash or tutorial, right? Which can totally be about hair and can be about other things too. Repeated this analysis for a number of other labels. I'll show you one more. Luxury cars, exactly the same visualization. So again, we look in the upper left, we see Maserati, we see Porsche, we see, you know, Chevrolet, you could argue that, but again, these are unambiguously cars, and most of them are luxury cars. In the upper right, we see words like turbo and driver, again, review. This is really encouraging. So after I saw this, I thought, okay, there's some signal here. I could probably do something with this problem. So the next step is featureization. So featureization is the process of taking your unit of work, which in my case is a video, and extracting information such that it can be presented to the machine and used for machine learning. So again, we have the same video. So what are some of the things that I use for featureization? Obviously, the video itself. So this is the audio, the images, everything we can use here. Then we have other signals. The duration, the title, the number of views the video has, its channel and publish date, its description, any comments users left, the video quality, its likes and dislikes, and the related videos. And we extract some from all of these in order to featureize our video. And how you do this is very important. This is where myself and my team spend most of the time, is dealing with this concept. So after we did featureization, we wanted to say, how do we actually measure the quality of our algorithm? So the metric that we settled upon was called average precision. So this is the integral of the precision recall curve. I promise this is the only math I have in my presentation. And basically it's a ranking metric, and it's a way to say how well did the algorithm surface the best videos in a ranking situation. Because that's what we ultimately have. We want to rank videos by every label. Okay? And this does it regardless of the depth within the list. There's other metrics like normalized discounted cumulative gain, which favors the top. So we didn't want to do that, so that's why we used average precision.
Really quick, how did you measure video quality in the previous video?
Oh, that's just something provided by YouTube. It's like standard definition or high definition. It's just an enum. Then we have to find a way to go ahead and average the average precision across all the labels. We chose mean average precision. And this is important because we want the quality of the labels to be all equally contributing to the overall metric. So then I compared two different learning frameworks. On the left is one probably most of you have heard of, TensorFlow with Keras as a wrapper. And on the right is something maybe you guys haven't heard of. It's called Valpil-Wabbit. Terrible name for a very nice piece of software. Full disclosure, I'm a contributor to Valpil-Wabbit. It's a large-scale linear learner written by John Langford, formerly at Yahoo, now at Microsoft. I recommend you guys try it if you guys have not played with it. Obviously, TensorFlow is a deep neural network. So what we did was we compared those two on 255 labels from ZEFR that had coverage in the YouTube 8 million dataset. Here are our results. Maybe this is surprising to some of you, maybe it's not. The linear learner actually beat the deep learned in this particular case. So I will say a couple of caveats. One, I am pretty much an expert in Valpil-Wabbit and certainly not in TensorFlow. The network architecture we used was a 3-layer neural net on TensorFlow with an embedding layer, a gated recurrent unit or a GRU, and then a dense sigmoid. In Valpil, we used 28-bit hashing, so that's 256 million features, 5-pass, cost-sensitive one against all. I can get into those details later if you guys want exactly what that means. But basically, for the data we had, Valpil was better, right? And so this is textual features, I should say. So the literature in textual features, deep nets are not outperforming other models as badly as they are for images, as they are for speech, excuse me. But as I said before, this data set was not released for the purpose we're using it for. It's actually released to further computer vision research. So as a result, at CVPR this year, YouTube partnered with Kaggle to have a competition to see how well people could understand their data set using a slightly different metric than what we used. They used global average precision. And this is one integral for all labels. Okay? And what you'll see here is the top results. So their global average precisions, 0.84 was kind of the top, 0.85. This was very interesting. And we wanted to see, well, how well did we stack up against these results using the same metric? And I should note that I specifically did not choose global average precision to judge myself, because you can think of this as having a bias towards those examples that have, those labels that have more examples in the test set. I don't care how many examples are in the test set when I'm going to sell this. So everyone who contributed to this had to publish a paper. I went through all of them, and some people of their own volition did publish their MAP. Here's were the ones that I found. Again, we beat them. So Rank U is number 6 here. The other two, DL 2.0 and Inform Lab, were below this fold. So it could be that some of these tops did beat us. I don't know. But at the very least, we're competitive. Okay? And so what I want to answer is kind of why this is in this particular instance. And so to do that, I'm going to use a motivating example. Here is another YouTube video. This is Usher, a rapper on the left, and James Corden, a late-night TV host on the right. James Corden has a bit, if you've never seen his show, called Carpool Karaoke. He drives around town, he picks up celebrities, and they sing in the car. If you were doing purely computer vision, that means all you had was the video itself. What might you extract from this video? That it's about cars, maybe that it's about Range Rover specifically if you had a great classifier because they're in a Range Rover. Maybe it's about driving, Los Angeles, singing. If you had amazing facial recognition, maybe you'd recognize they're both celebrities. Well, yes, it's about all those things, but what it's really about is carpool karaoke. That's so big on YouTube, it's its own thing, and people want to buy that as a concept. And look at the title of the video, Usher Carpool Karaoke. It doesn't get much more clear and easy than that. Any algorithm could pick that up. And so I'm bringing this up as a motivating example because it's important in your domains to not always just go after the sexiest thing. Like, I want to do image processing, I want to do video processing. If you have to, if you're Nokia or you're Apple and all you have is the image, yeah, you have to. But most situations have many modalities that you can fuse together. And pick the one that's the easiest. So with that being said, we wanted to compare the deployment of Keras with TensorFlow, again, just on the textual features, with Valpo-Wabbit. First, the training time. It's much longer to train a deep neural net than a linear model, just a fact of life. It's also much more expensive. You need fancy GPUs to train a deep learning model. VW works on my laptop. I can literally do all the training right here. Scoring cost, again, you need GPUs or TPUs for TensorFlow, and it's cheap to score Valpo. And totally my own bias, we just understand Valpo better. So with that being said, deploying the Valpo solution was more sensical for us. Obviously, your mileage may vary, but this is what the decision we made at this time. So I want to do a brief aside on how we do supervised learning in production. And I know there's a talk in the afternoon on this, so I'm just going to do very brief here. This is actually a topic I'm very passionate about. I could do a full hour on this. So I'm going to do kind of how we actually go about doing this. So I'm going to introduce two classes of people. On the left, we have my 4-year-old daughter's favorite Muppets, Beaker and Honeydew. And on the right, we have Margaret Hamilton, who worked for NASA in the 60s. She actually coined the term computer scientist. So our Muppet friends are going to stand in for our data scientists, and Margaret Hamilton is going to stand in for our data engineer. So the Muppets care about that for any one example, the best label is returned, or the best labels are returned, right? Margaret Hamilton cares that for all examples, we score them efficiently. She cares about things like logging and monitoring and uptime. Beaker and Honeydew care about things like average precision or NDCG or you know, that kind of stuff. And so the way that we unify these two groups is with an interface. So the interface is called model. It's very simple. It has two type parameters, A and B, and it's merely a function that goes from A to B. In this case, the A is our video, and the B is a set of labels. Right? We return a set of labels. And the data scientists are concerned with only the interface and below, the implementation. And the data engineers are concerned with only the interface and above. How do I call it? And once you realize this is a very natural separation boundary, you can just supply the model. And so we actually train every night. I get a Slack notification every morning saying, hey, congratulations, you trained a new model. We didn't lift a finger. Totally automated, goes right to production. It's really nice, and it's almost a requirement in our domain because of model drift. So model drift is this notion that the distribution you're modeling changes throughout time. And we know that's very true on YouTube. What's popular on YouTube today is not going to be popular next month, next year, right? So we have to have constant retraining. In order to facilitate this, we have an open source project called Aloha. It was developed primarily by Ryan Deek, who was at eHarmony at the time with me, now works at ZEFR with me. It is a Scala DSL, domain-specific language. The real nicety that Aloha provides is it subsumes the feature functions. So what that means is one of the problems we had at eHarmony was that we would have matches, but we'd have to extract information out of the matches, just like we do with videos, to present them to the machine learning engine. And that code was constantly re-implemented. The data scientist would write it, and my predecessor used Perl. Don't ask me why, but that's what he liked to use. He would write these Perl feature functions, give them to the Java engineers, and say, do this again. Mistakes all the time. Really hard to catch mistakes, too. And some of them weren't even mistakes. Some of them were the fact that the languages were just different and treated floating point numbers slightly differently. But what Aloha does is it has the feature functions as part of the model. So our native type, our type A, is the business value, the business object of a video, which we use Avro. This also supports protocol buffers. It supports JSON. And these are not data science specific objects. They are business specific objects. And it's really powerful because we plug in real nice. So you guys can check this out if you like. I encourage you guys to do that. And so what's the real takeaway from the production side is that before we had Aloha, we did the more traditional data scientist setup, which is the data scientist would get a bolus of data, they'd have some kind of SLA overnight or something like that, they'd score it and return it. Well, this led to production issues. Data scientists are not data engineers. Their skill sets are different, right? And so invariably we had one person on the team who would be woken up at 2 in the morning, once a week, once every other week, something didn't work. He would be the only one responsible for it. Now, we don't have production issues. We just publish models. We don't score. If the model doesn't score, it's not data scientist's problem at 2 in the morning. Now, maybe it is at 10 in the morning during a work day. We'll work together, but that means I don't need a pager, which is really powerful because if anyone here has ever had a pager, you know they're terrible. So this is how we productionalize. And like I said, I can go into much more detail on this. If you guys are curious, come find me later. I could talk your ear off about it. So let's switch gears and talk about how we do this from the bottom up. So this is all for the supervised learning, the top-down approach. When we're looking at bottom-up algorithms, what we were interested in is finding algorithms that could handle a large number of documents or videos, and that could be retrained and rescored quickly. Again, we have model drift. And it works well with text. We're again focused more on the metadata. And what we really want is descriptive outputs of topics. So if you guys are familiar with the literature, by the words I chose to use there, you can probably guess what the next slide is. Latent Dirichlet Allocation, and I know I butcher that middle word all the time. LDA. So for those not familiar with LDA, it is a very well-studied generative algorithm, originally published by Michael Jordan, not that Michael Jordan, out of Princeton in 2003. The original paper has been cited 20,000 times. An online variant was developed in 2010. And it basically has everything we need. Now, I should mention this is definitely an older algorithm. And there are much more sophisticated deep models out there. DocNade comes to mind. I was just actually at NIPS where they're presenting a plethora of different solutions. So certainly we could get better. But this one is very well studied and well implemented. And what we wanted to do was say, hey, can we get something out to be judged? And if it's great and successful and we want to productize it, we can then iterate. So again, we have to do feature extraction. Just same exact slide as before. The difference is now we're focused solely on the textual-based features. And when we do that, we see we have title, description, comments, and related videos. And I want to pause here to talk about how difficult this process was. And I don't think this is LDA specific, although I don't have a lot of experience with some of the deep models. But what we struggled with was how to featureize these. So what pre-processing to use? What stop words to remove? That was a big one. So a lot of people in their descriptions love to write, follow me on Facebook, or here's my Instagram handle. And you would get the Facebook topic and the Instagram topic. The algorithm was right. That was a topic. It appeared all the time, but it was meaningless. So removing those as stop words really helped. And the other big issue that we have is that YouTube is in basically every language on earth. So we have to figure out how to do text processing and data processing and stop words, not in English, not in just Spanish, not in just Japanese, not in just Hindi, not in just name your language. It's probably there. And so we had to deal with all of these different things in order to get something reasonable. And these are all hurdles that we had to overcome. And again, I don't think it's LDA specific, although I don't know for sure. So with that being said, I compared two different implementations of LDA. Valpil has its own implementation, actually written by the author of the 2010 online variant of the paper, and Spark. So Apache Spark is a very nice distributed processing pipeline written in Scala. I love it. I know that's controversial to say, but I really like it for embarrassingly parallel stuff. So if you're trying to map over a collection or call reduce, it's glorious. I've had mixed results with its machine learning implementation, but its LDA implementation was actually really nice. And this is what we used. So in order to show the results that I'm going to do next, it was all Spark with Spark's LDA. So what we did, yes?
I'm just curious, how did you deal with the multiple language?
So, right, so we did stop words in many languages, and this involved a lot of research of my own, going out and like scouring the internet for stop words in all these different languages. And then we had to simplify our processing pipeline a lot. So we made use of Stanford's Core NLP for some of the processing pipeline, and basically you could have like the simple one, which is like capitalization and then removing punctuation and stuff. And then if you could detect that it was English, and we had an OK language detector, you could go more with English. Or you could do lemmatization and stemming and that kind of stuff. It's still absolutely a work in progress. but these are concerns you have to have. So here are some results. So the first thing I did was I took LDA and ran it on our entire corpus. And what you'll see here is a visualization of one topic out of, I think this had 50 or 100 topics, I'm not sure the exact number. The red bar represents the term frequency for the topic given. The blue bar is the overall term frequency. So words like review and love are frequent in the entire corpus. So after looking at this, what I did is I went and looked at the top videos in this topic as well. And this is a topic about unboxing your iPhone. Cool, definitely a thing on YouTube, not a question. I looked at another topic from this same model, and here's one that's about hip hop, right? Totally a topic on YouTube, right? And this was, we didn't tell the algorithm any of these things existed, it found it on its own. So some pros and cons of this. First, the pros. Like I said, it's an actual representation of what is on YouTube, which is really powerful. Cons. The topics do not necessarily correspond to anything we want, and frankly, ZEFR has been professionally watching YouTube for 6 years. These were already known to us. Like unboxing is popular on YouTube, hip hop is popular on YouTube. So the next thought I had was, well, what if we could use LDA to surface only trending videos on YouTube? I define trending as the ratio of the number of views today divided by the number of views last week. Took the top 5% of videos according to that metric, ran LDA again. Here's one of the topics. So probably staring at this for 10 seconds, you could guess what this is. This data was obtained on September 1st of this year. Game of Thrones, right? It's a Game of Thrones topic. It's very clear. The top videos were all clips of Game of Thrones, right? Awesome. Very insightful, very useful. So some pros of this is, again, it's an actual representation on YouTube, and the topics do evolve constantly. But we have the same con that they don't correspond to anything our customers necessarily want. They probably want Game of Thrones, but the topics evolve slowly. And so Minecraft is perpetually popular on YouTube, always trending, and it has been for the last couple of years. And so these topics can evolve very slowly. So the last insight that I had was, what if we used LDA to surface only trending videos within our higher level packaging? So we know these are things that the user wants. So just to remind you, here's the same video from before. Our top level packages are in green. So if we took all the videos that rolled up to a green package and ran LDA within there, so we threw away all the labels. I did that. So I'm going to show you two. The first is our all movies package. So here you can see all movies in green and the corresponding labels that we have that you can go buy if you're a client of all movies. here's one of the topics I found. So nowhere does it mention Jason Statham or Vin Diesel, but this is a topic about the fate of the Furious, which is a popular movie that came out in the Fast and the Furious franchise that's all over YouTube, and clips of Jason Statham and Vin Diesel are very popular, and you could validate this by looking at the top videos on this list. And it was just very, very interesting, and this is something, if you want to buy all movies, this is super useful to you right now. Repeated this analysis for millennial women. So we see millennial women in green on the bottom right. It has a lot of labels in common with millennial men, so you see both of them. So go ahead and look at that for just a second. You get a feeling for what we think of when we think of millennial women. And I'm going to show you one of the topics we found for millennial women. Indian street food. I see food. I definitely see food in the labels, but certainly don't see street food. Certainly don't see Indian street food. So this is something that our customers could want. It is super valuable. And so we really want to figure out, and this is still not in our product yet, but it's important to figure out how can we surface this information. And there's a lot of nuances because these topics that I picked are obviously very nice. Some of them are not so nice. If you guys are familiar with some of the recent Facebook stuff, you'll know what I'm talking about. And they do require some human curation, probably before we show them to our end clients, but there's a lot of value here. So just to sum it up, YouTube, the data is difficult, right? If you guys have dealt with Twitter data or Facebook data, it's probably very similar, super messy, many languages. I watched a talk recently on data science with emojis. I can't believe that I watched that talk. Dealing with these mixed modality signals, go after the easiest thing, right? Don't be fancy when you don't have to. And finally, unsupervised clustering is very powerful, and it gets exponentially more powerful when you tie it to some business value you already have. Thank you very much. Do I have time for questions? I have 2 minutes? 3 minutes, sorry. I have 3 minutes if everyone has any questions. Yes? Yeah.
But now you have multimodal modality of data, like in content field, can be in sound, in text, embedded in a video, or in comments. How do you cluster those together in your LDA model?
Right. So basically what we did is we represented the video just solely through its text. So we found, like I said, we had like title, description, related videos, and comments, and the aggregation of all those into one document in LDA words was kind of how we did it. Nope. All right, so can we go to the back and we'll come back? Okay.
Hey, John, just a question about the LDA, because I know you mentioned there were certain 200 topics or something like that. How do you choose the number of topics in clusters? Something whichever.
So the question was, how do we choose the number of topics for LDA? That is the question with LDA, right? The one that everyone has to answer. There are algorithms out there like hierarchical LDA, but frankly, this was just a guess and check kind of thing. I mean, the way that we had was, I had a cadence with experts on YouTube where I would go and say, okay, I'm going to try a bunch. I'm going to look through it qualitatively. We used Perplexity, but again, it didn't really mean a lot to us. And then basically, like every week, I'd sit down with these experts and be like, what do you think? And they would tell us, oh, this is not a topic. This is 2 topics. It's really just, unfortunately, it's how it is when you're in a totally unsupervised domain. So.
I'll just talk loud. So you're talking about Apache Spark, also a big fan, so we could be in the next. So with Apache Spark, from a data visualization perspective, do you have a preference when you're dealing with, especially on the machine learning side, like a Databricks or something like that on the Apache Spark side?
Right, so the question was on visualization for Apache Spark. I'm personally not a huge visualization guy, so I really don't have an opinion on their visualization tools. All of the visualizations I showed in my talk are all cited, so I think, are the slides going to be distributed? So the slides are going to be distributed. You guys can find everything that I did. It's all Python-based. So a lot of it was recommended to me, actually. So, and I think that's it. Thank you guys very much.